We actually have one more kind of limit to evaluate before we get to the calculus concepts that we want to get into. And this is a limit at infinity. And so you can see here in this definition, we're going to be looking at what happens as I let my x values get as large as you want, that is, go as far down the x-axis as you want, or go as far down the x-axis in the negative direction as you want. And what this is saying is if my y-coordinates, my f of x, becomes arbitrarily close to some number L, then we're going to say the limit as we go to infinity or minus infinity is equal to L. And so the idea is, as I'm way out here or way out here, I'm looking at my my graph, my y-coordinates, and if they are approaching some value, say 1 or whatever, L, as I go out here. Now, they can do whatever they want in here, but as I get closer and closer in here, they start getting closer and closer to this value L. Then we're going to say the limit as x approaches infinity, even though we can't ever get to infinity because infinity is not a real number. But what you're saying as you go out towards infinity of that function, we'll say that that's equal to L. And likewise, we do the same thing over here. If it's going to some value, some other value as I come out way out this direction, and it can come in there any way it wants to, then we would say here the limit as x approaches negative infinity. And whatever this is. So this time let's say it's m of this function would be m. So that's the notion we're going to cover here. These are called limits at infinity. As I said, you can't ever actually get to infinity because it's infinity. But that's what we're going to call it. And we're going to then extend that to say, well, then this must be this line, y equal L. That line's a horizontal asymptote. And I remember an asymptote is a line that sort of looks like it attracts your graph, or your graph, as you go farther and farther along that asymptote, your graph starts looking more and more like that asymptote. So that's sort of the geometric feel behind it. That's how it's related to the graphs. So if we look at our basic functions, we have some functions with horizontal asymptotes. For example, any of the 1 over x graph, 1 over x to a power, we know that this graph looks like this. And so I know that the limit as x goes to infinity of 1 over x, looking at the graph, you can see it's getting closer and closer to 0, but just looking at algebraically, I'm going to be putting big numbers in this denominator, which is going to make this go to 0. So y equal to 0 is a horizontal asymptote. I'm just going to abbreviate that, horizontal asymptote. And the same thing happens if you go to minus infinity. It just happens that all the values are negative, but it's still approaching 0. It's just coming from beneath 0, but still verifies that y equals 0 is a horizontal asymptote. Now, they don't have to go to the same thing when you go into positive and negative infinity. In general, functions can do different things. And this is true for 1 over x to any odd power. That it looks sort of like this, remember? So they all look like that. And it's also true for 1 over x squared. Just looking at the graph, we know that the graph looks something like that and that. In both cases, as I go out to infinity or negative infinity, it's approaching 0. Those y coordinates are going to get closer to 0. So 1 over x to any power has y equals 0 as its horizontal asymptote. If I look at a function like e to the x and take the limit as x goes to infinity of e to the x, well, the graph of e to the x looks like this. And if I'm going to infinity, then it's going to infinity. So we can get infinite values out of this. It's telling me what's happening. This limit doesn't exist technically, but it is telling me, yeah, it's getting big. So that's not so helpful. But if I go the other way, if I go to minus infinity, we can see that what I'm going to get in this case is it's going to get closer and closer to 0. We can see that from the graph. You can put actual numbers in and you'll see that's going to happen. Because you're going to be putting negatives in, which gives you 1 over e to those powers. And the bigger that negative number is in the magnitude, then the closer and closer you get to 0. So this one also has a horizontal asymptote of y equals 0. And so all the exponentials where the base is bigger than 1 have horizontal asymptotes of y equals 0. And it turns out the ones where the base is less than 1, like 1/2 to the x, Remember, those get flipped around this way. Oops. Those are exponential decay. But still, as I go to infinity this time, I'll still get 0, not negative infinity. If I go to negative infinity, the graph's going to infinity. But this will also have a horizontal asymptote of 0. So all the exponential functions have that. But 0 is not the only asymptote that you can have. We can go to infinity for tangent inverse. And based on the graph, tangent inverse, we know, has these asymptotes of pi over 2 and minus pi over 2. And so that means this is going to go to pi over 2 if I'm going to infinity. And if I'm going to minus infinity of tangent inverse, what's going to happen is it's going to get closer and closer to minus pi over 2. So this one has two asymptotes, y equal pi over 2 and y equal minus pi over 2. Those are both the horizontal asymptotes. So we can have more than one, don't have to have any, and they can be different in different directions. Turns out you can't have more than two, because if you had more than two, you'd somehow be approaching two different asymptotes in one direction, and you wouldn't have a function anymore. And then we have functions that don't have asymptotes. For example, if I try to take the limit as x goes to infinity of natural log of x, well, based on the graph of natural log, or any log where the base is bigger than 1, that's going to infinity. And if I can't even go to infinity, negative infinity, so it wouldn't make sense to try to write that limit. Any x to the n, as we go to infinity, on x to the n, all of those will go to infinity, because all those graphs on this side sort of look like that. It just depends on how steep and whatever. If I go to negative infinity, it does depend on whether I'm doing the even functions, which look like that, or if I'm doing the odd functions, which look like that. So if n is odd and I go to negative infinity, so if I go limit as x goes to negative infinity of x to the n, I get one of two answers. That's an n. So x to the n there. If n is odd, I get negative infinity. And if n is even, I get positive infinity. And then I guess the only other thing is we've got some that have other weird properties. So if I try to take the limit as x goes to infinity of sine x, what's going to happen there? Sine x just does this forever. And so I cannot say with any consistency what this value is going to be, right? I mean, it's not approaching a value L as the definition requires. The definition said if my values get closer and arbitrarily close to some value L, then we're going to call that the limit as we go to infinity. So this one never will get close to some arbitrary value. It's also not going to infinity of any kind. It's just bouncing around between -1 and 1. So this one we just simply say does not exist. So it's one of those infinite oscillations, but it's stretched out. It's not like the oscillations we saw before, because I'm going all the way to infinity. It doesn't matter if it's stretched out infinitely. So sine and cosine, they're both going to give you those oscillations. So neither one of those limits are going to exist. So that's the idea of an infinite limit. It's actually very important in several places in the calculus sequence. Just trying to determine what happens long term in terms of my function when I let my x's get as big as you want on the x-axis or as negative as you want on the x-axis.